Hola amigos, bienvenidos. Welcome back. In this video, what we are going to do, we are going to discuss a special method that has been developed to solve MIP problems, mixed integral programming problems. This approach is called branch and bound, and really is a very simple and a beautiful idea about how we can use linear programming to attack MIP problems. And if you want to go further into methods to solve MIP problems, I really recommend this book, Integral Programming by Michel Conforti, Gerard Cornelius, and Giacomo Zambelli. So what we are going to do here in this video, we are going to start by defining a MIP problem. And we are going to use this MIP problem to explore the branch and bound method. So the problem that we have here is we have two variables, x1 and x2. These variables needs to be non-negative and they need to have integer variables. And we have two constraints, minus x1 plus x2 less than equal to 2 and 8x1 plus 2x2 less than equal to 17. And we have an objective function which is linear and that we want to maximize. So this is the original MIP problem that I'm going to use to illustrate the branch and bound method. Now let me define another problem that is related to this original problem, but it's going to be defined in the following way. The name of this problem is going to be P0, and this problem is going to be called the LP relaxation of the MIP problem. And why it's called the LP relaxation of the MIP problem is that because we are going to consider all the constraints of the original problem except the constraint of asking for integer values. This problem will contain all the integer solution of the original problem, but we are not requiring to have integer solutions. So let's in this first part of the video, I'm going to explain the method using in a graphical way, explaining how the branch and bound method works. And in the second part of this video, I will to use a more algorithmic approach, but you will have the understanding of the graphical way of the branch and bound. So our P0 is the LP relaxation of the MIP problem. P0 has the constraints of the first constraint, which is defined by this variable, and the direction of feasibility is defined by this green arrow. The second constraint is defined by this red line, and the feasibility direction is defined by this arrow. These two arrows define the non-negativity constraints. So the LP relaxation of the original MIP is all the solution, all the points that we have inside this trapezoid are a solution of the P0 problem. But observe that all the integer solutions are included there. We have more solutions, but all the integer solutions are part of this P0 problem. That's why we said that P0 is the LP relaxation of the original MIP. The solutions of the original MIP are all these blue dots that we have here. And the objective function is to maximize this linear expression, and the direction of optimality is defined by this green arrow. So if we use this direction of optimality, it can easily be seen that the optimal solution is defined by this red dot. So what is the optimal value of the LP relaxation? P0 is x1 1.3 and x2 equal to 3.3. And the optimal solution value is 14.08. And observe that the solution has fractional values. So let's explore what is happening here. So notice that the objective function value of 14.08 of the LP relaxation defines an upper bound of the original MIP. Why? Why is an upper bound? Because it is possible that an integer solution might be close or equal to this thing, to this 14.08 value, but no integer solution will be higher than this value. So that's why this 14.08 value defines an upper bound of the original MIP problem. And the value of the decision variables are fractional, x1 equal to 1.3 and x2 equal to 3.3. And so this solution is not feasible to the original MIP problem. So what we are going to do is to take the LP relaxation P0 and define two new problems. So the new problem that we are going to define is going to be called P1, which will take all the constraints of P0 except the integrality condition, and we are going to add this constraint x1 less or equal to 1. So basically what we are doing is we don't want this solution to be part of it. So what is the closest integer from below that are closer to this solution? Is to have x equal to 1. So any solution that is equal or less than 1 should be an integral solution that we need to consider. So that's why we add this constraint. P2 is also defined in terms of the problem P0, but we add the constraint x1 greater or equal to 2. And observe that x2, that the 2 value is the closest integer from above associated with x1. So any other integral solution of x1 is going to, it can be greater or equal to 2. So in this particular way, we have partitioned the P1 problem into two subproblems, and these subproblems, the union of these two subproblems contain all the integral solution of the original problem. And this process of partitioning the original problem into subproblems is called branching. So again, our original problem is defined by this trapezoid that we have here. This trapezoid, it defines all the LP relaxation of the original problem. So what we are going to do is to define two problems, P1 and P2, by adding two constraints. So the first constraint that defines the P1 problem is by considering the P0 problem, which is all this trapezoid, and then adding this constraint, x1 less than or equal to 1. So x1 less than or equal to 1 is defined by this red line, and the direction of feasibility is given by this line. So we get a new trapezoid, but it's smaller than the previous one, and see that in this part we contain all the part of the integral solutions of the original MIP. And we are going to also define a new problem that we call P2, which is equal to x1 greater or equal to 2. And this problem contains also the other part of the integral solution. So observe that with these two subproblems, the optimal solution of the P0 problem, which is the LP relaxation of the MIP problem, is not longer a solution of neither the P1 problem or the P2 problems. And also observe that if you take the union of P1 and P2, is this region here and this region here, this little triangle here, you will see that the union of these two problems contain all the integral solutions. So if we explore these two problems, it is possible that we might find the best integral solution of the original MIP problem. And also notice that the intersection of P1 and P2 is empty, and that's how we are eliminating the optimal solution of the LP relaxation. So let's now solve P1 using this objective function. So now we get this solution as the optimal solution. So we get x1 equal to 1 and x2 equal to 3. Eureka! This is an integer value for the problem, and the objective function value is 11.8. So this is very good news. We have been able to find an integer solution just by using linear programming. So let's now solve the P2 problem. And remember, this is the direction of optimality. So if we solve this problem, we will get this new optimal solution. And the optimal solution in this case is x1 equal to 2, and oops, x2 is equal to 0.5. And the objective function value is 12.05. So let's analyze a little bit the information that we got now related to solving these two problems, P1 and P2. So the problem P1 is a LP relaxation. But even that is a linear programming relaxation, we were able to find an integer solution. So that's why I was so happy, because the branch and bound approach was able to identify an integer solution. And the optimal objective function value of this problem P1 is 11.8. So we will say that this value of the objective function of 11.8 is a lower bound of the originally MIP problem. Why is a lower bound? Because it is possible that the other problem, P2, might have a better integer solution. So at this point, the best solution that we have is 11.8, but it is possible that we might have a better one. So that's why this number is a lower bound to the optimal solution of the original MIP problem. But since the solution that we got now, x1 equal to 1 and x2 equal to 3, is integer, there is nothing else to do with this problem. And in this particular case, we say that this problem is pruned by integrality, meaning that there is nothing else to do with this P1 problem. So let's now explore what happened with P2. P2 is also an LP relaxation, but in this case, we don't get an integer solution. We get a fractional solution because x2 is equal to 0.5. And the objective function value of P2 is 12.05. And we say that this is a tighter bound of the original MIP problem. Why? This is going to be an upper bound because any integer solution that we might have for the original MIP problem, it might be equal to this number or less than this number. So this number of 12.05 represents an upper bound to the optimal objective function value of the original MIP. And this notion of bounds are very important because they will help us to prune or cut the tree that we are generating when we solve the branch and bound problem, when we are using branch and bound. Since the solution that we get is no longer integer, we need to further explore this problem because it is possible that this problem might contain the optimal solution of the original MIP problem. So let's explore now P2. So how we are going to explore P2? We are exploring P2 because the objective function value is larger than the best solution that we got from the integer solution that we got from solving P1. So that's why this problem P2 is worth exploring. But we have a fractional value of x2 equal to 0.5. So we need to branch on this variable x2. And to branch on this variable, we are going to generate two subproblems for P2. One of the subproblems are going to be P3, which P3 will contain all the solutions, integer or fractional, of P2, and we add this constraint x2 less or equal to 0. And P4 is going to be P2, but also considering the new constraint of x2 greater or equal to 1. So now let's go back to the graph and see graphically what is happening. So in this particular case, the problem that we are exploring is P2, which is represented by this small triangle. And observe that this P2 has only one integer solution there. So, but we don't know that. Mathematically, we are not seeing this problem as we are seeing with this graph. So we need to mathematically identify if this problem contains an integer solution that is better than the best integer solution that we have developed so far. So let's add one of the constraints to this P2 problem and generate a new problem P3. So P3 is P2, is this triangle, plus this constraint. But the feasible direction of this constraint is defined by this green arrow. So really the feasible set of solution of P3 is defined by this tiny line here, which is the base of this triangle here. So P3 is just defined by this line, and P3, observe, contains the integer solution of P2. And we are going to use this objective function here, where the optimality direction is defined by this green arrow. So if we do that, when we solve these problems in the feasible region is defined by this line, boom, we get this number. But, oops, very bad. Well, not very bad, but it's not good, because x1 is fractional again. The optimal solution of this problem, given this objective, is x1 equal to 2.125 and x2 equal to 0. x2 equal to 0 means that we are in this line, okay? And x1 is equal to 2.125. And the objective function value is 11.6875. So let's analyze. Let's add now the other constraint related to, no, let's analyze what is happening with the P3 before we go and solve the P4 problem. So when we solve the LP relaxation of P3, we got a fractional value, but observe that the objective function value of P3 is 11.6875. And this value, this 11.8, is an upper bound of the best integer solution that we might get to solve this problem. And observe that the best integer solution that we got by solving the problem P1, that value was 11.8. And that gives us an integer solution. And this new value that we got from P3 is an upper bound to any integer solution that we might get there. But this value, this upper bound, is worse than the best solution that we get from solving the problem P1. So this problem cannot contain an integer solution that will be better than 11.8. So in this particular case, we say that this problem doesn't need to be explored anymore. Why? Because this problem doesn't contain an integer solution that is better than the best solution that we have identified so far. So let's now see graphically what is problem P4. So problem P4 will be P2 plus a new constraint, and the new constraint is x2 greater than equal to 1. So see what is happening. We have defined a problem that requires solutions that are defining here, and also requires solutions that are defining here. But there is no solution in this triangle and in this quadrant here that belong to both constraints. So there is no solution here. So P4 is empty, meaning that there is no solution that can satisfy all the constraints that defines P4. And in this particular case, we say that the problem has been proved by infeasibility. So in this first section of this video, I have illustrated graphically how the branch and bound approach works. So in the second part of this video, I'm going to use a more algorithmic approach to show how branch and bound works. But now you can relate when we say we are solving this problem. You now have the graphical representation of how branch and bound is solving each of the subproblems that we have here. So we are going to break now here, and in the next section we are going to explain a more algorithmic way of solving this problem using branch and bound. See you next time.